Okay, we're going over practice quiz 3 here, which covers 6.1 to 6.3. This is going to be two separate tapes. One of them I'm doing it using a table that you can see off to the right. That's the appendix table for Z values. And then the second video that I'm going to make is going to be specifically for problems 4 and 5 and 6 that you can do on a TI-84 graphing calculator. So you might want to watch over both of the videos. It's up to you. All right. Problem number 1. Problem number 1 and 2, by the way, are out of section 6.1. So problem number 1. Specifically, this involves the empirical rule, a diagram of which is in your notes, and it's also on page 275 in your textbook. So you might want to refer to that empirical rule, okay? The incubation time of chicken eggs is normally distributed. The mean mu is 21 days. Standard deviation sigma is 1 day. We have 1,000 eggs that are being incubated. How many chicks do we expect to hatch in 20 to 22 days? Notice the mean is 21. Notice from 20 to 22, you're adding and subtracting 1 standard deviation. So you're doing 21 plus and minus 1 standard deviation, right? So that's our mean, plus and minus 1 times sigma. Well, according to the empirical rule, we can expect approximately 68% of the data to fall within 1 standard deviation of the mean. 68%. That means we expect 68% approximately of those 1,000 eggs to be hatched. So if I change 68% to a decimal, 0.68, and I multiply that by the number of eggs there are, I get 680 eggs. So we expect approximately 680 eggs to hatch in that 20 to 22 day range. Problem number 2, control charts. The out of control signals for a control chart are on page 279 in your textbook. On a control chart, if a point falls beyond 3 standard deviations above or below the mean, is the process in control or out of control? That's signal number 1 on page 279. If you have something that falls even 1 point beyond 3 standard deviations, it is out of control. So be sure if it's formed like a word problem, like I did problem number 2, or if I give you an actual picture of a control chart, you can look at it and tell whether or not it's in control or out of control. Problem number 3. This is out of section 6.2. In section 6.2, you need to be able to change an X value, a raw score, to a Z value, and you need to go the other way too. You need to be able to change a Z value back to the original raw score, the X value. These are on page, the formulas for those are on pages 289 and 280. Or 290, excuse me. And they're also in your notes. All right. The mean mu is 10. Standard deviation sigma is 2. We want to find the Z score. Notice that your X value is 12.5. The formula we're going to use is on page 289. Z equals X minus mu divided by sigma. So that's going to be 12.5 minus 10 divided by 2. And I'm going to do that on a calculator here real quick. And I get, hold on. Typed it in wrong. I get 1.25. That's the corresponding z-score. Problem number 4. It helps to graph these out on occasion, so take a look here. Here's the z distribution, the mean of which is 0. That means negative 2.20 would be back here somewhere. Positive 1.30 would be on the positive side somewhere. Why I did that, I don't know. Anyway, positive 1.30. All right. We want to find the probability z is between those, right? So what we're going to have to do here is find the area in the tail below negative 2.20. Find the area in the tail below 1.3, and then subtract the larger area from the smaller area. So you'll notice on my z table right here, I'm already on where it's left shaded, where it's a negative z value, right? So I'm going to go down to negative 2.2, which is right here. At the top, I'm going to go to where it's 0.00, and I get 0.0139. For that 1.3, I'm going to go to the positive z table, where you have positive z values, right? To the right of 0. I'm going to go down to 1.3 and across at the top where it's 0.00, and I get 0.9032. So this probability is going to equal to 0.9032 minus the 0.0139. Because what we're looking for is this region right here. We want to know what is this area under here, right? And so on a calculator, I'm going to do 0.9032. And I'm going to subtract 0.0139. And I'm going to get 0.8893. Problem number 5. If you're doing this using the chart without the graphing calculator, you're going to have to be able to change the x values to z values. And we already did that in a previous problem, right? So the probability 7 is less than x is less than 9 is going to equal the probability that. Now we're going to standardize the 7 and the 9. So we're going to take 7, the x value, minus the mean, which is 5, divided by the standard deviation, which is 1.2. And now instead of it being less than an x value, we change it to a z value. And that's going to be less than the x value 9 at upper bound, minus the mean 5, divided by the standard deviation of 1.2. And we're going to round these to the hundredths place. 7 minus 5 divided by 1.2 to the hundredths place is 1.67. You round to the hundredths place so you can use the table. That's going to be less than z. That's going to be less than 3.33 on the upper bound. Okay. Once again, I'm going to draw a picture with this. Oh, and I did it incorrectly. Give me just a sec. So 1.67, let's say it's right here. And then 3.33, let's say it's up here. We want to find the area between them. So first we need to find this area to the left of 1.67. We're already on the right table because these are positive z values we're working with, right? So I'm going to go down to 1.6 and across to 0.07, and I'm going to see where they meet, and they meet at 0.9525. Then for the 3.33, I need to find the area to the left of that. So I'm going to go down to 3.3. It's way down here towards the bottom. And then I need to go over to the top at 0.03 and see where those meet. They meet at 0.9996. So the area that we're going to be looking for is going to be 0.9996 minus the 0.9525. Grab a calculator and do that. You get 0.0471. Okay. Then finally, problem number 6, find z such that 95% of the curve lies to the left of z. So here's my standard normal distribution. I want to find the z value such that this area off to the left is 97.5%. I'm going to write that as a decimal. That's equal to 0.9750. Notice in the guts of the table here, they carry it out to the 10,000th place, 4 decimal places, right? So what I want to do is look in the inside of the table, and I want to find the closest thing I can find to 0.9750 and check this out. This is exactly the table, 0.9750. It's at 1.9. And then to the 100th place, it's 6. So we get z equals 1.96.